Okay, can everybody see my screen and hear me? Good. Hi, my name is Ciara Conway. I am a PhD student in the Shusha Lab at UNC Charlotte. And today I'm going to be briefly talking about my research towards prediction of unknown lipids, which was done in conjunction with the Unknown Lipids Working Group. Just to give some background, the purpose of the Unknown Lipids Working Group was to conduct an untargeted lipidomics analysis across different labs given varying sample types, and then align those features for each metabolite. So that kind of yielded this alignment ID that we could then use. So there's a lot of questions we were trying to answer from this analysis, but the one that I focused on was, can we annotate some of these unknowns? And to the right, I have a proposed workflow that I created to try and annotate these compounds. So I started with all the aligned data, specifically focusing on the positive ion mode spectra. And for each alignment ID that did have an MS2 spectra, I put that through NIST and MS Finder. I then had the entry keys returned, which I put through classifier to further classify those compounds to at least get a superclass or class possibly. We either parsed out the SMILES or generated them from PubChem REST API, which those SMILES would then go into the similarity clustering module. And so I'm going to go into detail now about this workflow. And the first part of it is I'm going to actually talk about the parsing steps and the library search steps. So for the MSP file generation, we had an original file given to us along with this spreadsheet here, and I used the retention times and the M over Z values to match to the MS2 information so that we had this new MSP file of all of the unknowns. So all of these spectra were then put into the library matching, and for the library matching, we used MS-PEP search, which included the NIST 20 MS2 libraries. In addition, we added the monolipid blast to expand the number of lipids we could match against. It was also then put through MS Finder. And in the purple boxes down here, you can see the threshold scores we used along with the hits that we returned. And then after that, which chemical identifiers came back from each software, and then how we obtained all the SMILES. So the next part I'm going to talk about is the similarity clustering steps. So for the clustering, once we had those SMILES, we converted them to the fingerprints and used those to generate a Tanimoto similarity matrix using an 85% similarity score. Once we had those similarity scores for the matrices for each alignment ID, we then used hierarchical clustering using complete linkage within the Python SciPy package to generate these clusters. And we looked at the largest clusters for each alignment ID to see if we could generate some substructure motif. And if that wasn't possible, using classifier to at least determine the compound class. So this is kind of the analysis we did. To the left, you can see a breakdown for each tissue type of the type of superclass that came back for the compounds. In the green are the lipid or lipid-like structures that came back. So that's about like 40% of the unknowns, which is pretty interesting. So not only are we trying to fill out this lipidome chemical space, but we're also now picking up not just lipids or conventional lipids, but another array of chemicals coming back. So that was pretty interesting to see. The graph below actually shows a stack plot of all of the classes of lipids that came back for each tissue type. And then to the right is actually one of the analyses we did for a particular alignment ID. In this case, there were 29 results that came back for this particular compound from the search algorithms and MS Finder. And the largest cluster is cluster 1. You can see that both identity and hybrid search came back and they converged to the same compound in this case. And cluster 3, which is our second largest cluster, we brought in, and then which only had hybrid search come back. But again, the functional groups are similar. And the only difference is that hydrocarbon chain in the middle. So at the bottom is actually the proposed substructure that we kind of converged to when looking at these different clusters. And it is important to know MS Finder did come back with results. The only difference was instead of the cyclohexane, it was an adamantane group on the end. So this kind of just shows how we can possibly validate our results that we're getting back by bringing in multiple softwares to try and find these compounds in different types of softwares. And it's also important to note that this is not the end of the improvements we're making to the pipeline. And we're also trying to add in more search algorithms and softwares to try and elucidate some of these unknown compounds. So thank you very much. I'm willing to take any questions, and I would like to thank the DO Lab for allowing me to be a part of them, and also the Unknown Lipids Consortium. So thank you.
Okay, great. I mean, I actually think we have time for one question, or it can go into the chat. Okay, so Katrina, you got a question?
Yeah, I would just like to ask a question. Ciara, do you see a number of compounds So the compound you showed was, you know, lipophilic, but
Mhm.
something that we wouldn't consider as a traditional lipid in that sense. Do you see a lot of those potential hits? Can you do like a, I don't know, like a summary statistical analysis using classifier or something like that to see how many of those types of molecules are showing up?
Yes, I can. I'm actually working on that right now, and I was able to generate a pivot table. So it's actually just now going in and seeing which ones are biologically relevant and those that may not be seen naturally. So yes, there are a lot though that we probably would not consider to be like common lipids, which is really cool to see.
Yeah. The reason I asked is we had a lot of points that fell outside of our eye mobility data in terms of the confidence interval per class. And I'm just curious if we were to look at some of the M over Z values for some of these, could that explain those outliers that we're seeing?
Okay, yeah, I can actually get you the data. Put it in a table.
Awesome. Yeah, thank you.